Okay, so let's revisit alpha decay just a little bit. And if you remember, alpha decay has a Greek symbol that looks like the fish symbol, right? And we practiced drawing it last week. But basically, you just draw, I draw a fish. Okay. These particles are actually a helium nucleus, which makes sense because if you take away the electrons, the atom's then going to be positively charged, right? So basically, all an alpha decay particle is helium, no electrons. Okay? They are kicked out of the parent nucleus. So basically, remember, when there are too few or too many electrons, the parent nucleus is unstable. So what they're going to do is they're either going to try to gain or lose neutrons to become more stable. Well, in this way, we're going to throw out a helium. So are we gaining or losing neutrons? We throw out a helium. Losing. Because a nucleus contains protons and neutrons, right? So what he's doing is he is throwing out neutrons. He's trying to get rid of a few things. Okay? These allow an unstable nucleus to decrease both its number of protons and the number of neutrons. Because remember, conservation of mass says we can't lose protons or neutrons. We can transform them, we can move them to somewhere else, but they never just disappear. So this parent nucleus in this picture down here, which I have as uranium, it currently has 238 protons plus neutrons. Okay, well, uranium's really unstable. That's why it's a radioactive material we often use for nuclear power plants. It tries to become more stable. So in one way, he is going to emit a helium. So if you're losing 2 protons and 2 neutrons, then your parent has to change, right? So it's no longer going to be uranium, it's now going to be thorium. If you look at the periodic table, uranium's at the bottom on the very, very last row. He's number 92. If you lose 2 protons, you then become number 90, which is thorium. So he is trying to become more stable. Is thorium stable? No. So thorium's probably going to go through the same basic concept. He's going to try to lose neutrons to become something else. And it's just kind of like a chain reaction. But these are alpha particles. Again, are alpha particles very dangerous? No.
No.
Okay. All right, so what about the electrons? So I said that alpha particles are positively charged. They don't have electrons, right? Well, where the heck did they go, correct? When alpha particles leave the parent nucleus, it only takes 2 protons and 2 neutrons with it. So therefore, he is a charged particle, right? If you don't have any electrons, nothing to balance out those protons, you are going to have a positive 2 charge, which, again, makes sense because it's helium. Helium has 2 electrons. If they don't go with him, he's going to have positive 2. So therefore, if he gets kicked out, and he's an ion now, is the parent nucleus very stable? No, because now he has too many electrons. Okay? They're trying to change their neutrons, not their electrons. Electron changing is ions. So if he kicks out a nucleus and no electrons go with him, he's kind of fixing one problem but kind of causing another one. And so what happens is the alpha, who is now positively charged, will steal 2 electrons from somebody, who will then in turn steal 2 electrons from somebody, who will then steal 2 electrons from somebody. And this continues until they go back to the parent molecule, and then those 2 electrons are stolen. So this process actually happens relatively quickly because when you release a helium, you're probably not releasing it very far from the parent nucleus. So it kind of sets off a chain reaction of electron stealing until somebody next to the parent steals those 2 extra electrons. And this is called ionizing radiation because in order for the radiation to happen, we have to form ions. And then a whole bunch of ions get formed in the process of trying to fix the mistake. Remember last week when we were doing balancing equations, sometimes we had to make one problem before we could fix it. Same concept. They make a problem trying to fix it, and so then they have to fix the second problem. All right, so this is the process that's dangerous. So the process of stealing electrons is what affects our health. Emitting an alpha particle is not that big of a deal. It's the electron shifting back and forth that is what causes damage to your cells and to your skin and so on and so forth. Sometimes the electrons that are stolen come from the electrons holding your molecules together. Well, if you break the molecules in your DNA, that's bad. Okay? Your DNA is held together by hydrogen bonding. If you're breaking some of those bonds, you're going to be altering your DNA, essentially. So if you break your DNA up, the cells from that point forward have a missing, because remember, DNA is kind of like instructions, correct? For how to make cells, for how the cell to process. So if the DNA is now broken, it's not going to give correct instructions for how to make cells, and this is how we get cancer. This is how we get mutations in your DNA. Okay? Do you think you can avoid all forms of radiation, though? No. All right, so now let's spend a little bit of time talking about beta decay. Beta decay, again, is the Greek letter. It looks like a B with a tail, correct? These particles are actually electrons, which makes sense because they are negatively charged. So if we remember back to last week, or not last week, Tuesday, we learned to put the mass number in the top left. So the mass of an electron is 0 technically, right? The charge of an electron is what? One electron has what charge? Negative. Which usually we put the number of protons in the bottom, but since an electron is the opposite of a proton, that's why we put -1. So this is what a beta particle looks like. Electron, no mass, -1. However, these are not a normal electron from a shell. It's not like one of the electrons is picked out of one of the surrounding cells. In a beta decay, a neutron from the nucleus turns itself into a proton. And remember, neutrons have no charge. So if it's becoming positive, it has to have something that is also negative, right? And so what it does is it actually starts off, which you can see down here in the picture at the bottom, it starts off as a neutron. Neutron has one mass unit and no protons. And it's going to break up into a proton, but conservation of mass, right? If we have a 0 atomic number on the left, we have to have a 0 atomic number on the right, correct? Well, 1 and -1, doesn't that equal 0? Yes. So if I turn this off, you guys can see it a little bit better. But yeah, so the numbers on the top have to be equal to each other, the numbers on the bottom. So 1 minus 1 equals 0. 1 plus 0 equals 1. Okay, so basically a neutron is just separating itself out. All right, so let's look at a beta example. And I know that this is a little hard to read up here at the top because it's black, but it wouldn't let me change the colors. So we have to look at the conservation. If we look at carbon up here at the top corner, carbon has 6 protons. How do I know that? Because I can see it on the periodic table. It has an atomic number of 6. Atomic number tells you we have 6 protons. However, this is carbon 14, not carbon 12, right? Carbon 12 is what's listed on the periodic table. So if it has 14 mass units, how many neutrons does it have? 7. Or what's 14 minus 6? 8. So 14 minus 6 protons gives us 8 neutrons. So on the left, we have 6 protons, 8 neutrons, and 6 electrons, right? We have to have the exact same number on the left side. So I kind of just turn the arrow into an equal sign. We're all pretty decent with algebra. Okay, so if we have 14 on the left, we have to have 14 on the right. Well, here's 14 plus 0. Does that equal 14? Yes. Then we have 7 minus 1. Does that equal 6? 7 minus 1. So conservation of mass. So if carbon is going to emit an electron, it is going to turn into nitrogen. Does everyone see how I did that? A little bit? Okay. All right, so let's look at another example, one that you can see a little bit better. There you go. Tritium, which is hydrogen 3, an isotope of hydrogen. It has a mass number of 3 and an atomic number of 1, which means it has 1 proton. So if we do 3 minus 1, we have 2 neutrons, right? Okay, so whatever we have on the left side, we need to have on the right side. Conservation of mass, correct? So if you look, I have a big question mark right here. We need to figure out what element we are going to have when hydrogen goes through a beta decay. We need to know what element we're going to end up with. So, honestly, again, treat this like a little algebra problem. 3 has to equal something plus 0. What? 3. So this is going to be 3 on the top. The 1 on the left right here has to be 1 on the other side. So if we have -1, what minus 1 is going to give us 1? 2. So then we put a 2. Then we look at the periodic table. Who has an atomic number of 2? Helium. So this question mark element that we're trying to solve for is helium. Is it the helium on the periodic table? No, because helium on the periodic table has a mass of 4, so therefore this guy is an, what's it called? Isotope. This is an isotope of helium. Okay. Hydrogen was a parent nucleus. Helium is the daughter nucleus. So this is what the equation is going to end up looking like here at the bottom. And again, all I did was a little bit of algebra, right? Whatever's on the left has to be on the right. So just do a little bit of algebra, not hard algebra, just a little bit of algebra. So now let's look at gamma decay a little bit. Gamma decay occurs when the nucleus kicks out pure energy. Okay, energy specifically in the form of light, and it is not always visible to the human eye. Okay, we can only see a small portion of what we call light, correct? All right, electromagnetic waves with very short wavelengths, less than 10 picometers, which is really small, and we can only see 400 to 700 nanometers. So gamma radiation is a lot smaller than what we can actually see. So can other animals possibly see it? Yes, because we can only see the visible light spectrum for 400 to 700, but that doesn't mean that other species or other animals or we can see it with instruments that can pick up on that type of radiation. Okay. Gamma decay, because it's not matter, because it's energy, because it's just a form of light, it does not change the nucleus of the parent. It honestly just goes along with other types of decay. So if I throw out a helium nucleus, if I throw out a beta particle, I'm probably going to also release a little bit of energy, because that's the whole point, correct? So this is also a type of ionizing radiation because they are energetic enough to knock loose some of the electrons. So if we look down here at the example I have, we see iodine on the left. Ooh, sorry. We see iodine on the left, and we see iodine on the right. Are these the exact same form of iodine? Yes. And then, you can't see it, but over here it says plus, it has the gamma signal. So that's saying that it's releasing gamma radiation. It's releasing that type of energy. But since gamma radiation is not matter, it's not changing the parent molecule. It's just getting rid of some of its additional energy. Okay, so alpha rays are least harmful, right? Beta particles are in the middle. Gamma rays are the most harmful. But the question is, which one is worse for you and your health? Well, it honestly depends on where the radiation is coming from. If the source is external, alpha and beta particles most likely are not going to get past your skin. So could they cause maybe some issues with your skin cells? Yes. But they're not going to harm your internal organs, most likely. Gamma radiation, however, can penetrate your skin, so it has more chances of targeting the organs and your major functions of your system and causing some health effects, right? However, let's say that the source is internal. Okay. A helium atom has 2 protons, 2 neutrons. Gamma particle is technically no matter. So if the radiation is internal, which one's bigger? Your helium or your gamma? Because helium's technically not even matter. Their helium's going to be bigger, so it's going to be a lot more harmful inside your body because it's going to damage your tissues. It's going to damage your cells because it is so much bigger. Now, is the gamma radiation going to hurt you too? Yes. But it's just going to possibly affect your DNA, whereas the helium are going to physically cause damage to your cells. And so it's just kind of, it's all in how you look at it. All radiation is bad for you, but it's just in what. Well, actually, you know how when you go have like, I'm not a nurse or a doctor, nor did I take English classes, so I don't know they're correct. But like when you know to get like an MRI, don't they usually make you drink something ahead of time? What's it called? Barium. They make you drink barium. Well, barium's radioactive. So basically you're drinking radiation, and that's what the machine is picking up on. The machine is picking up on those radioactive processes releasing energy, and that's what it sees. And so that's an example. You eat, I mean, uranium's in the soil outside. So if you, I mean, I don't think you guys go out there and eat dirt, but it happens. You know, your food grows in the ground, right? And so you probably eat more dirt than you actually realize. And so you eat it all the time, and it enters your body different ways. And so it's just, again, you don't eat enough of it for it to cause enough damage, and you don't go get MRIs every single day. If you went and got an MRI every single day, that would probably be bad. Okay, so, the next type that we're going to talk about is something called electron capture, and it's not one of the three main types of radiation, but it is one of the types. This is what atoms do when they have too few neutrons. So remember, all atoms are trying to become more stable. They're trying to lose and or gain neutrons to achieve this. Electron capture is what they do when they are trying to gain neutrons. Okay? It is the opposite of beta decay. So beta decay is basically an electron, right? So if this is the opposite, it's basically a neutron. You add it to a proton to create a neutron. So, for example, a neutron turns itself into a proton and an electron and then emits the electron. The nucleus then takes the electron from the first shell and brings it into the nucleus and combines it with a proton. So if we think about the beta decay that we were just dealing with, in beta decay, if you remember, our proton, or our neutron broke apart into a proton and an electron, right? So after beta decay happens, electron capture is like the next step. The next step is, well, now I need more neutrons. I need something. And so what they do is they kind of like reach out and they grab the electron from that first energy shell and bring it back into the nucleus. And there's protons in the nucleus already. So this electron kind of combines with the proton. It's like they slam together. And in the process, they create a neutron. So this is the opposite of what happens in a beta decay. In beta decay, we take a neutron and it splits apart to form a proton and an electron. An electron capture, an electron from outside the nucleus slams into the nucleus, combining with the proton to create a neutron. So they're the exact opposite process. Okay, so when we do this, nothing seems to change because the number of electrons didn't really change. They're still there. The matter didn't change. So how do we know that it has occurred? If we aren't using anything else to add to the nucleus, if the nucleus is just stealing things from around it, we have to look at what happens to energy-wise. So when it steals that first shell electron is removed, an electron from an outer shell takes its place, and then an electron from past that takes that place. It's like a chain reaction. It keeps stealing electrons until there's no more electrons to steal, and then it causes it to lose energy. And the energy that is then emitted is what we know as an X-ray. So this is how they take X-rays of your body to see your bones. So an example of this would be argon-37. Argon-37 has too few neutrons. So if you look up at the periodic table, argon is supposed to have a mass of 40. Here he has a mass of 37. So how many electrons has he lost? 3. So he doesn't like that. He wants 40 because 40 gives him pretty close to a 1-to-1 ratio of neutrons to protons. So everybody wants that 1-to-1 ratio. That is stable. And so what he's going to do is he's going to try to steal some of his electrons to make his a little bit more stable. So if argon steals one of his electrons from that first energy level, remember conservation of mass, what's on the left must be on the right. So then if we do 18 plus a negative 1, we get 17, right? If we do 37 plus 0, we get 37. If you look up number 17 on the periodic table, we see what element? Chlorine. So, and 17, we're trying to get a little bit, we basically in the process, we lost a proton, honestly, right? And so our ratio from protons to neutrons has improved a little bit, correct? Did we actually gain a neutron? No. We theoretically lost a proton. We're forming a different element, but it's fixing the problem. We want our ratio of neutrons to protons to be better than it currently was. If we can't physically gain a neutron, let's lose a proton and see if that helps anything. All right. The next example is a positron decay. Positron sounds a lot like what? Positive. So we're probably going to be dealing with something that has a positive charge. A positron decay is a particle that has the same mass as an electron, which is basically nothing, right? Electrons have a mass that's so small it's negligible. So if it has the same mass as an electron, it honestly has no mass. But instead of having a negative charge, it has a positive. And so another name for this guy would be an anti-electron. It's the opposite of what an electron is. And it looks like this. Okay, when we're writing our equations, that's what we're going to put in it. This is actually very similar to an electron capture. A proton gets turned into a neutron. However, remember how in electron capture we were stealing electrons? That doesn't happen. So if we're not stealing electrons, we're releasing the mass of a proton, but it can't have a negative charge. So we call it a positron. Okay, this type of decay has a very, very short lifespan, and they actually destroy each other. And in the process, when they destroy each other, but they kind of like collide. Okay, and since they're both positively charged, what's going to happen? They're trying to repel each other, but they end up colliding. So in the process, when they collide, they release a whole bunch of energy, and they release it in forms of gamma rays. And this is called an annihilation reaction, which we'll get to in just a second. Okay, so here is a nice pretty picture, because I think you guys like my pictures, or I hope so. An annihilation reaction, again, is dealing with a positron. So basically what happens is, here we have a positron, here we have an electron. They are attracted to each other because one is positively charged, one is negatively charged, right? And so when they collide, they're going to release a whole lot of energy, hence the green flashing out. And in the process, they are going to release not one, but 2 gamma rays of energy, which makes sense. If two things, think about car crashes. What happens when cars crash? Isn't a lot of energy released? Which is why the car becomes mangled. Sometimes it catches on fire, a lot of heat, right? That's all version of energy releasing. Well, if an electron and a positron, even though their masses are so small, they're still going to release energy, and they release energy in the form of gamma rays. For those, I know a lot of you are going to school to become a nurse, and this is actually what they do in PET scans. And so he talks about that a lot on page 107, but I really feel like I would confuse you if I went into that detail. So I would read about it a little bit on page 107.
Is that the same kind of concept as what the super collider thing does that everyone sets arms about, smashing everything together?
On a much smaller level. But yes.
What?
Okay, so we are done with types of radioactive decay. We've talked about 5. Okay, so now we're going to go into the little bit of math. And so let's talk about a half-life. Because based on how much radiation is released determines how harmful it is, right? Okay, if it only releases 1 gamma ray, you're good. If it releases 10,000 gamma rays, I'd run for the hills. Okay, so when we're talking about how fast something is releasing radiation, we use the term half-life. Okay, this is the rate things are decaying. And when I say decaying, I'm talking about the parent molecule breaking up into a daughter molecule and some other sort of radioactive particle. Okay, so what is a half-life? A half-life is the amount of time it takes for half of the substance to decay into something else. So half of our parent molecules are now daughter molecules. Okay, so does that mean everything is decayed? No. But however much time it takes for half of them to decay into different atoms. So this can actually range from fractions of seconds to billions of years. So if something is decaying if half of a sample can decay in a fraction of a second, is that going to be bad? Yes, it's releasing a lot of particles really fast, correct? If it takes it 8 times 10 to the 24 years, so billions of years for it to decay, is that very harmful? No, because it's releasing one decay particle maybe every 10,000 years. So we only live for 100 at best, right? And so most likely are we going to come in contact with one if it only decays once every 10,000 years? Probably not. So let's do an example. If you have 10 grams of an isotope, so you have a sample weighing 10 grams, and its half-life is 1 year. After 1 year, you should have 5 grams of your sample left, right? Did the other 5 grams disappear? No. They're the daughter atom now, so they're still there. The mass is still there. They're just in a different form. After 2 years, you're going to half that sample again, right? So you had 5, now you're going to have 2.5, correct? Do you still have 10 grams of mass total? Yes. Now you have 2.5 of your parent and 7.5 of your daughter, whatever it's decaying into. So let's say we go into a third half-life. This is how I like to do it. I'm going to take this away for just a second. But we had 10 grams. Its half-life equals 1 year, correct? So at 10 grams, if we're going to half it, after the first year, we're going to have 5 grams, right? After your second half-life, you're going to have 2.5. So after 2 years, you're going to have 2.5 grams left. After your third half-life, you're going to have 1.25, right? And you can just continue to go on and on and on and on and on, right? This will continue on and on and on, but are you ever going to technically reach 0?
No.
No. But let's say I stand up and I go halfway to the door, and then halfway to the door, and then halfway to the door, and then halfway to the door. There's going to become a point where I can no longer go halfway to the door, right, without crossing the door. So theoretically, no, we can never actually get to 0. But in all actuality, eventually, that has to happen. Okay. All right, so remember, atoms are very, very small. So in a sample, we could easily have millions of atoms. So after 1 half-life, you should have half your sample left. After 2 half-lives, you should have 1/4 of your sample left. After 3 half-lives, you should have 1/8 of your sample left. And then 1/16, and then 1/32, so on and so forth, right? So you technically never get to 0, but eventually the sample would be too small to measure. Just like I would eventually have to cross the door. I could no longer just keep going halfway. Okay. This limit is usually 10 half-lives. Usually after 10 half-lives, your value is going to be so small you can't measure it anymore. So after 10 half-lives, your sample has technically fully decayed. So if we look at this data or this chart, basically at the top we're starting with 100% of our product. And then if you notice, as you go down, it starts to kind of level out towards the bottom. Are we technically ever going to cross 0? No, but it starts to get so close to the bottom that we can't even see it anymore. All right, so just like we talked about which of the rays is more harmful, right? Alpha, beta, gamma. We determined, well, it kind of depends on how you look at it, right? Well, which is more harmful, a short half-life or a long half-life? Well, again, it depends. So let's think about it. let's say a short half-life, that's 1 day. So say we have that 10-gram sample we were just talking about, and it's releasing radiation every single day, right? So technically, we could put it in a lead-lined box. We could put it in the corner and say, nobody mess with that. It's radioactive. But after 10 days, most of it, the majority of it has decayed, right? So is it going to be reactive anymore? No. Right? But at the same time, it's releasing radiation really, really, really fast. Things that have long half-lives, like 100 years, okay, let's say we have that 10-gram sample. Well, it's one of its atoms is releasing radiation maybe once a week, maybe once every other week. So it's not releasing radiation very quickly. But do you think I can put it in a box and set it in the corner, and for the next 100 years, technically times 10, 1,000 years, tell nobody to mess with it because it's releasing radiation? That's a little bit harder to do, correct? Because no one's going to be around for 1,000 years. And we have to, secondly, where do we have space to store things for 1,000 years that isn't going to affect businesses or schools or whatever? You know, I don't have a room that I can just store stuff in and not go into it for the next 1,000 years. So again, it's kind of how you look at it. Things that have long half-lives don't release as much energy or as often, but at the same time you have to store them for a lot longer. So then we start having issues where, so right now we're trying to determine how to utilize nuclear energy for nuclear power plants. But what are we supposed to do with the radioactive waste? Where do we store it? Where it's not gonna hurt anybody for the next thousands of years. Okay. Do you think we can avoid all forms of radiation? No. There's stuff called background radiation. Okay, a Geiger counter, which is hopefully I'll get one in the next week and we'll be able to do that lab. A Geiger counter is an instrument that detects radiation. It will always detect radiation because, like I said before, uranium's in the soil outside. So occasionally it's going to reach its half-life, even though uranium has a really long half-life. An atom is going to decay here and there, and so it's going to pick it up. Now the chances of that harming you are not as high, but you do encounter it on a daily basis. It's also in the air that we breathe. It's also in the water that we drink. Okay, all of these things you can intake, but at the same time, if they have a long half-life, the amount of time it takes water to go through your system is not very long. So maybe it won't even go through its half-life by the time it exits, right? Okay, this exposure is dangerous, but at the same time, your body has really good repairs. And so, yes, you might come in, your skin is going to encounter radiation from the sun, right? This is what causes skin cancer. But as long as you're not outside every single day, and as long as you don't go in the tanning bed every single day for an hour, your body can repair it relatively quickly, and so you're not going to get skin cancer, hopefully. Now, it depends on your skin type and all of the other stuff. But if you take care of yourself, you should be fine. Walking to and from your car is not going to kill you, right? All right, so let's just look at this giant chain reaction. Okay, let's see if we can identify some of the different types that we had. So we're talking about alpha, beta, and gamma. So let's look at what happens. We start with thorium. We're ending with radium. 90 minus 88 is what? 2. 232 minus 228 is what? 4. Looking at the periodic table, what has an atomic number of 2? Helium. So what type of decay happened between thorium and radium? What type of decay is represented by helium? Anyone? Alpha. This is an alpha decay. So now radium is still not stable. So he's going to try to decay again. So now let's compare him to number 89. So we start with 88. We go to 89. That's not conservation of mass, right? So 89, how am I going to get from 89 to 88? Right? So negative 1. 228 and 228 is 0, correct? What has no mass but a charge of negative 1? An electron. So what type of decay is this? Beta. You guys kind of starting to pick up on the process? Okay, Now we're in number 89, and it's going to increase again to thorium. How do we go from 89 to 90? Right? Technically negative 1 because it's on the right side. So 90 minus 1 is going to equal 89, right? Okay, and then again 0 because 228 and 228 are the same thing. So what again is 0, negative 1? An electron. What kind of decay is this? Beta. So now we're back to thorium, correct? To what? Say that again. Because it's technically on the right side. We're starting with actinium and we're ending with thorium. Well, we have to do conservation of mass, and so we can't magically gain, so it has to be negative 1 on the bottom. And we're going to do lots of examples here in just a minute. Okay. Let's do one more. So now we're at thorium again, but it's a different thorium than what we started with, right? The first thorium had a mass of 232. This one now has 228. So we're trying to fix the neutron problem. Okay, now we're at thorium, and again, oh, we lost 2 this time around. We went from 90 to 88. That can't happen, right? So then we put a 2. We went from 228 to 224, so that is 4, which again is a helium. What type of decay is helium? Alpha. We're back to radium. Is it the same radium we had before? No, the first radium had 228, the second one has 224. So you guys see how this is a chain reaction? I bet you it's going to go helium or alpha, beta, beta, alpha, beta, beta, alpha, beta, beta, until we finally get into something that is stable. And if you notice, he keeps going, 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 and then we get to lead. Lead is stable. And so he stops. Lead is now stable. His protons, his neutrons are all stable now, and he can stop being radioactive. He no longer is going to decay into anything else. So, I'm going to do some practice problems with you here in just a minute, practice with the math, but your homework is page 111 through 112, number 1 through 16, and